So welcome, everybody. Thanks for being here again. This is once again another seminar of the Quantum Spain series by TalentQ. And we are very glad to greet today Benedikt Poggel. I hope I pronounced it correctly. Benedikt studied physics at the Karlsruhe Institute of Technology and the Ludwig Maximilian University of Munich, with a focus on the theory of condensed matter and first contacts with quantum computing. Since 2022, he has been doing his doctorate at the Fraunhofer Institute for Cognitive Systems, which with a PhD habilitation, Jeanette Lawrence. His research focuses on the reliable application of quantum-based solution methods to optimization problems. Today, Benedikt is going to give us a seminar on his recent papers, and the title is Quantum Computing with a Purpose: How to Decide When a Solution Path is Beneficial. So thanks, Benedikt. The floor is yours. Remember, if you want to make a question, you raise your hand, and then we will switch on your micro, and so you can ask. Anyway, this will be 45 minutes as usual, plus questions at the end. Benedikt, thank you very much, and the floor is yours.
Okay. Yeah, thank you for this invitation. I'm very happy to be here and to give this short talk. Like actually not so short, on our latest paper, or one of our latest papers on optimization. I will also give you somewhat of an interview of an overview of our activities at Fraunhofer IKS in our group. So yeah, you kind of get the full picture. And if you have any questions, I trust Javier to manage those and tell me if there's something, because I won't be able to see you. Okay, so first let me start with a brief introduction, like on why we are even asking this question. Okay, is the slide switching? No, perfect. When I started my PhD approximately 3 years ago, we were tasked with finding good solutions for optimization problems, good quantum-based solutions. And so we tried out the algorithms that were sort of the major hopes then, which were variational algorithms, so something like the quantum approximate optimization algorithm, or VQE. And we kind of expected that they would be able to solve just normal optimization problems. So what we looked at is some traveling salesperson problem. So basically finding the shortest route that connects a number of cities and then returns to the origin, and try to solve that. And when we did that, we saw that the results really were not at all what we expect. They were awful. And so we dug deeper into this matter and discovered something that you see on this plot here, that if you do such a variational training, this is what you see here. So you have the number of circuit evaluations on the x-axis, and the sort of physical Ising energy on the y-axis. This works quite well if you're looking at optimization problems that don't have any constraints. But the problem is, as soon as you have some complicated constraints, like we have in the traveling salesperson problem, you run into this issue where just the large majority of states is infeasible, so it doesn't fulfill the constraints. And then what you optimize and what your algorithm actually does is spending a lot of time in some areas that are just not relevant to the final result at all. And what you do from this is that we cannot actually look at Ising energies and then judge the quality of quantum algorithms only on this basis. Because you could reach very good Ising energies, like 99% approximation ratio, but for certain problems you will still be outside of the feasible subspace. And this is actually what we saw then in this is actually my first paper. So nice, we're going from the first to the last one now. That you have this sort of transition energy, where even for small TSPs you could you could look at this very clearly, and that you need to reach a very high approximation ratio. So remember that we're doing minimization here. So like the best solution is this red line here, and you want to, or you need to come very, very close to that to even start generating feasible solutions. Because what you see on the y-axis here is the feasibility ratio. So sort of the ratio of feasible solutions that you have to an optimization problem. And this is the first step that you need to do. And as you can see here, for like very small problems, for this 4-city TSP, the solutions are basically always feasible. And this axis starts at 95%. But then for larger, you see this nice threshold here, which is far below 90% approximate, or far beyond a 90% approximation ratio. And this was actually the reason why the standard algorithms there didn't really produce the results that we predicted there. Okay, what have we done since then? With this, I want to make a short detour and start by presenting you our activities in general in our group. And then I have a sort of a different topic, just as a brief spotlight, so that you can see how our sort of applied research in quantum computing can look like. And then we dive deeper into optimization. One of my major research topics was is the third block here, solution paths in quantum optimization, and finally, have quite some time to dedicate to our newspaper, or one of our newspapers, scalability challenges and variation in quantum optimization. Find this on archive, otherwise it's currently under review. Okay, quantum computing at Fraunhofer IKS. I assume that you're not all very familiar with the Fraunhofer Society, so I'll explain that briefly to you. We are a research society based in Germany with almost 80 institutes all over Germany. We also have dependencies in other countries, but we mainly in Germany. The important thing that distinguishes us from other research organizations is that our financing comes 1/3 base financing, 1/3 public projects, and 1/3 industry projects. And this means that we really need to do applied research, because otherwise industry won't pay us for our research. This is sort of something that the creators of the system invented in order to force us to really produce solutions that are close to industry. And that's actually, at least in Germany, this is a kind of unique setting. Then within these, from these institutes, my institute, the Fraunhofer Institute for Cognitive Systems, based in Munich, is a quite young one and also still a quite small one. We have something about 100 employees, founded 6 years ago, and have a focus on enabling safe AI mainly, or in general cognitive systems, with our sort of main business areas being in mobility, health, and automation. But one other topic that we are also looking at, of course, otherwise I wouldn't be here, is quantum computing. Within the whole Fraunhofer Society, we have maybe 15 institutes that are looking at different aspects of this. In our group, we have 7 people and a bunch of master students, a bunch of external PhD students. And what you will notice here is that we have a nice mixture between physics and computer science here. And this is sort of the expertise that you need to really make quantum computing solutions happen, because physicists are very good at understanding the quantum aspect, but usually not very good at writing a sort of real efficient software and knowing the ins and outs of that. That's why you need the computer scientists. And I have to apologize, this is a little bit of a bragging a slide now. These are basically our publications over the last few years, which you can group in some topics. A big part of the group is looking at quantum machine learning, various aspects of this. We will look at one particular example of quantum convolutional neural networks very briefly in 2 minutes. Otherwise, other sort of paradigms like quantum reinforcement learning, quantum Bayesian neural networks, quantum kernel methods. Since we want to really enable quantum computing, of course, we need benchmarking. We need to look at how noise affects the applications, and finally have some activities in optimization, which we'll dive in deeper today, anyways. Okay, this is somewhat of a more tidy overview over our activities. One thing that I should mention is that we don't build a quantum computer at our institute. We're not doing any hardware research. We are purely on the software side, and so sort of trying to connect end users to the actual benefit that quantum computing may unlock or can unlock, with a focus on robust quantum machine learning. So robust means that we want to guarantee that it's learning correctly. We want to guarantee its safety. On decomposition techniques, because quantum computing currently is always a hybrid computing paradigm and will remain so in the future. So you always need to do some problem decomposition, and typically you need to put some parts on a classical computer, other parts on a quantum computer. Application-driven benchmarking, evaluation and verification of quantum algorithms, and then a little bit also security of quantum machine learning. Okay. To make this a little bit more concrete, how applied research looks like for us, I have 2 slides for you on one quantum machine learning topic. And this is actually kind of a good example how we start thinking about algorithms typically, because we normally don't start with a method, but we start with an application case. And here the application is, broadly spoken, image recognition. More precisely, we're looking at I think CT scans here of breast cancer, with the task being to classify whether we're looking at a benign lung nodule or a malign one. Why is this something that we are particularly interested in? Because this is exactly a safety critical application, so you really don't want to make a lot of mistakes here. Then something that, or it has actually one aspect that makes it hard for classical machine learning. And it is that you cannot produce arbitrary amounts of data, because of course you cannot generate new patients at will, and you also don't want to generate images indefinitely just to train your algorithm. And so the idea was, okay, maybe this is something that we can improve with quantum assisted machine learning. What we did there is then program a hybrid quantum classical convolutional neural network. So hybrid quantum classical means that you have some quantum layers, some classical layers. We don't need to dive into details here, I think. Convolutional is actually a very nice trick, because you do not need to read the entire data in at once, but you sort of have a 4x4, for example, filter that moves over the image, and then you're trying to extract features here. The original idea of convolutional neural learning is that typically you're looking at local sort of features in your image and then try to generalize from there. So it's actually enough to look at these small windows, move it across the image, and then try to learn. For us, of course, the advantage is that you can use small quantum computers to do this. And this is what we did. We actually showed that it works. Here on the right side, you see the training process. I'm not sure whether you can see my mouse, but I'll just assume it. And with this research, we were able to pinpoint a little bit better, like where quantum machine learning can be a tool that extends the ability of classical machine learning. This is faster training, less training data required. This is exactly what we tried to achieve there. Then, of course, we need hybrid algorithms, and with a big advantage that you can sort of tailor the algorithm to the size of the quantum computer that you have access to. Of course, this is no production-ready solution here, but these are the kind of insights that we're looking for, because our vision is that quantum computing in the future will sort of complement the abilities of classical computing and not replace anything. Okay, but now let's go over to quantum optimization and start with a little bit of a broad intro into the topic. Okay, what is the application perspective on optimization? If you're talking to a mathematician, they will usually think about optimization problems in complexity classes. This is something like NP or P, and we have actually found out in theoretical computer science, and then even translating that to actual implementation, that this is a relatively good predictor on which algorithms are fast and which ones are not. The problem is that if you're really looking at applications, this pure thinking in complexity classes does not tell the whole story. And this comes actually from two sides. First, from the methods, that often you have heuristics or even exact algorithms that are bad in a worst case scenario, but in your average case work totally fine. One such algorithms is the simplex algorithm. This is a sort of relatively easy idea to solve a particular kind of optimization problems, linear programs. In the worst case, it still has a very bad runtime scaling, but in many practical cases, it works very, very well. And actually, it works that well that today, if you can reduce a problem to a just purely linear programming problem that you can solve then with a simplex algorithm, you can just assume that you can solve it efficiently. On the other side, if you're looking at problem classes, it is often not that easy to determine what are hard instances and what are easy instances. In some cases, it is even easy, such as for the traveling salesperson problem, where you have a problem that, in its general case, it's is extremely hard, but as soon as you go to a certain structure of the problem, which in this case means as soon as the triangle inequality is satisfied by your cities, which is the case in what you normally imagine as a TSP, then it becomes much easier. And in particular, what you're looking at here is like you want to know how hard it is to approximate solutions. What I want to say with this is that you always have to look into the details, and in optimization, we currently don't really hope for something that I would call broad quantum advantage, where you can just apply quantum algorithms for basically every optimization problem. But instead, we need to be very specific in identifying the harder instances and the specific parts of an algorithm where classical computers might have a hard time finding better solutions. So in brief, this is what we're looking for. We're looking at mathematical problems that first have a broad range of applicability, especially because currently there's a high sort of development cost in there, so that we're really looking for those problems where, let's say, 1% better solution already delivers a large value. For these problems, typically exact classical solutions are not what you would use because they're slow. Classical approximations can be very fast. And the question is now whether hybrid approximations can improve either the speed or the precision of these approximations. One example that we looked at a long time is vehicle routing, which is basically a more complicated traveling salesperson problem, namely one where you have multiple paths to go. For example, package delivery service, or actually the example that we started with was garbage collection. Okay, but what do we need to enable quantum computing in the sense that end users can really use it? For this, we would need some sort of capsulated software where you input a problem and you get a solution out. This is very simple. Now, currently, the thing is that to get to that point, you need to think about a lot of different things. Not all of them even have to do something with quantum computing, which in turn means that you need expertise in many areas. For example, you need to formulate the problem. For this, you might need a mathematician. You also might need someone that just knows the problem very well. You need to choose an encoding, then you need to decompose the problem, then you need to select an algorithm. And selecting an algorithm typically means that you also need to tune the hyperparameters. And then you can even start putting it on the quantum computer. And what we are looking into is this outer layer of problem formulation, decomposition, algorithm selection, because that is something that's actually often treated as secondary for quantum computing. But without this, we won't get this technology to a point that end users can really apply it. Because in the end, we cannot expect companies to hire only physicists or to educate their people to be able to write quantum algorithms. We need some sort of abstraction. And this is actually the broader context of the paper that I will present to you in a few minutes, that we are trying to design such an abstraction layer, where as an end user, you can basically put your problem in from the top, and then it trickles down through these decisions. You have a lot of decisions to make there, like, for example, here, what formulation, what algorithm, and then depending on which algorithm you choose, you might have other decisions there, and try to automate that. This is hard for many reasons. Actually, one is that nobody really implemented this kind of structure before. Just as a side note, of course, in classical computing, you need all of this as well. You need it in sort of a different way. Of course, you don't have quantum algorithms, but there's still a lot of abstraction involved in getting your actual C program to the hardware, of course. And this is actually one of the things that has made computing successful, that I, as a physicist, that has never looked into assembly language or instruction sets of processors, can actually make use of the computational capabilities of classical computers. And this is what you need to have for quantum computing as well. And the other thing is that in quantum computing, we actually don't know how these decisions interact. So in principle, before choosing a good formulation, you would need to know how large is your device, how is the noise model, to even judge like how many connections do I want to have between my qubits, how large will the circuit be. And this is what we're trying to do here. And we're trying to find ways to estimate the impact of lower level decisions without just trying out all paths, because that is inefficient. And our answer to how to look at this is actually coming back to the beginning. We need to look at the right metrics first. So we really need to see how good is the solution that the quantum algorithm delivers. And this does not mean estimating some physical Ising energies, but instead really going to application-centric metrics. And this is one example of this. This is the feasibility ratio, like how many feasible solutions does your algorithm produce. Okay, and now in the remaining 20 minutes, let us sort of have a deep dive in this paper. I think I didn't put the archive link here. We can probably put it to you later, and it should also be in the abstract. It's called Scalability Challenges in Variational Quantum Optimization. This is based on a master thesis that we had in our group until January, actually, and was actually a very nice example. And this is also something that we want to really turn into a software tool where you can then estimate whether a variational algorithm might be successful without just trying out all options. Okay, how does this work? First, let's go one step back. Variational quantum algorithms work like this. You have some problem Hamiltonian that and then you build an ansatz circuit. This is this parameterized quantum circuit that depends on parameters theta. And the idea is that this ansatz circuit is relatively shallow and relatively small, so it can already run without error correction. And this gives you a quantum function, or like a quantum circuit that can then estimate the loss function of some problem. You can use this for quantum simulation. You can also use this for combinatorial optimization. And then you basically wrap a classical optimizer around this and tell it to find the optimal parameters. So in the end, you get an approximation for the ground state of this problem Hamiltonian C. And this is then, depending on how your problem Hamiltonian was constructed, this can be the solution to your simulation problem or also the solution to your combinatorial optimization problem. We're looking at combinatorial optimization here. Okay. what are the problems with this approach? This is a nice idea, but especially when it comes to the action of the classical optimizer, we have a lot of results that point out things that you need to look at here. First, you need to make sure that the classical optimizer is actually capable of optimizing the parameter of your quantum circuits. In this point, baryon plateaus are actually a major issue. A major issue. Baryon plateau means that you have large parts of your loss landscape where the gradient is not clear, and so optimizers that are based on gradients won't find a direction on basically where to choose the next parameters. But this even applies to optimizers that work without gradients. Then we are relatively sure that quantum computing will not solve NP hard problems in general quicker. So the classical optimization is probably the step that remains NP hard. So the question is how good are the approximations that we can get? Then how well can you simulate circuits? Of course, you always have to pay attention that if your ansatz that should be simple, so you can execute it on small quantum computers. But if it's too simple, then you can also just simulate it classically, and then you don't need a quantum computer anymore. There are actually even more recent results that are linking some of these issues. Like if you can prove the absence of baryon plateaus, sometimes you can also use this proof to simulate the circuit classically. This is yet another thing where you really need to look into the details. And then something that people have turned or have started to show quite early is that you need to pay attention how your resources scale. So how many shots you need, how many parameters you need, how many layers you need of quantum ansatz, and then decide whether this is favorable or not. Okay. Of course, this comes down to one big issue of current era quantum computers, which is noise. And actually, in this study, we want to tackle, or we want to show a method or an analysis to judge whether a variational algorithm can be successful in the presence of noise. This was the original idea. And as an example, we took one novel quantum algorithm here that didn't have a name before we really looked into it. We then called it block encoding quantum optimizer. This is the paper from 2023. And this actually looked like a nice idea because it's a little bit different from a VQE-based approach. It only needs one measurement qubits. It's quite general, but the question is, does this does this algorithm actually work on sort of real applications, or at least closer to real applications? So how do we do this? We want to do a scaling analysis that basically looks at two parameters, both system size and noise level. And now, if we separate the variational algorithms in its part, we have the problem input, we have the quantum part, and we have a classical part here. And all of these influence the performance. This is the problem that I told you about before, that you also have in this decision tree, and when you try to find abstraction layers, that we kind of need to pull these apart. For this study, we actually fixed the problem input, and we do not work on real problem instances, but on a specific kind of QUBO matrices. QUBO means quadratic unconstrained binary optimization. This is basically the optimization problem that has a one-to-one correspondence to Ising models in physics. Then the question is, how does noise affect the output of variational quantum algorithms? And then in particular, how do classical optimizers perform on noisy quantum loss functions? This is the result that I will be presenting to you today. Okay. So to again iterate our methodology, we fix the input problem. then we look at the loss evaluation and how it plays together with the classical optimization. In the end, we look at how good are the results that we get. And what is the input? We're looking at random cubo matrices with negative diagonal. This is actually a detail that makes the problem closer to actually trade-winning salesperson problems, or in general constraint optimization. Because typically, if you have constraints, you need to encode them into this cubo matrix, and this results in your diagonal having negative values. The advantage of this and not taking real problem instances that it's easier to scale and that it's very clear on how you get the input problem. And then the loss algorithm, we look at the Benko algorithm, and actually we also look at VQE and QAOA. I won't explain to you how this algorithm works in detail because it's not really important for details of the study. Just that the goal of new variational algorithms is here and typically to get well-behaved loss functions. Then what is very interesting is how we look at the noise here, because we do not try to model the noise from the hardware side, but instead we sort of adopt the heuristic noise model. And this assumes that noise has a certain impact on the loss function. And we model this as additive Gaussian noise. We also looked at multiplicative Gaussian noise here. Actually, in many cases, multiplicative Gaussian noise is more what you want to look here. So you don't have an addition there, but a multiplication. But additive Gaussian noise typically is harder because it affects also those parts of the loss function where you're close to zero. So we actually looked at this in, yes, kind of a worst case model, but as you will see later, this actually doesn't matter that much for the results. And then we looked at a suite of optimizers. You will recognize a lot of these from your favorite Python packages, be it Qiskit, be it SciPy. One new one is this NGD, normalized gradient descent. This is a gradient descent variant that tries to take the step size in a way such that you flip single bits between two solutions in order to more efficiently travel the solution space. And this is actually something that was proposed together with the algorithm, so we wanted to include it here. Okay, and then at the end of this algorithm, we sort of translate this back to a solution bit string. And for this, we just look at the quantum state, and in the end, I will tell you more about the metrics in a second. Okay. What do we look at? This is the approximation index. Approximation index means we look at the most probable solution string. So like if you have a quantum solution, you have some strings 10 times, other strings 3 times. We look at the most probable of this one. Of course, this is a simplification because in real world, you would just take the best one of those strings. But we assume that if you scale this up, we somehow need to make sure that the most probable solution string is actually a good solution. And then we run this experiment a lot of times and see how many times is this best solution string actually a good solution to our problem. And then good solution, we can look at different success probabilities here. We call these p-opt, p99%, p95%. p-opt means, okay, we only accept the solution string if it's the optimal one. p99% means we only accept the solution string if it has a 99% optimal coast value. This is then basically an approximation ratio. And in the same way, p95%, if the solution has a 95% quality. Okay, then we did run all of these experiments, and this is the kind of plot that you get there. Now, if you want to look at this on the x-axis, you have the noise level. So this is basically this standard deviation of the Gaussian that you get from your loss function. On the left from 0 to then, very high values. And then color-coded, you have the optimality or the probability of finding optimal solutions in an empirical way. On the y-axis, you have the scaling with system size. And we're looking at one specific optimizer here. I actually don't even know which one, but the general picture is always the same. That for small system sizes, usually the optimizers can take in quite a big amount of noise, but then you get this relatively well-defined threshold where you really come from a success probability of around 80% to even 100%, and then this quickly drops to 20% or something like this. Then we do this for basically all optimizers, all noise levels, all system sizes. On top, you see these three different success metrics that I already showed you. This is just looking at the optimal bit strings, at the top 1% and top 5% bit strings. And as you can see, the images look somewhat similar. You have this clear boundary when moving to larger noise levels. Okay, and now we start with the actual scaling analysis. We fix the system size now. And then you can already imagine this. If you would put this on a graph now, you get some sort of sigmoid function. And these look like this. As you can see, there are some optimizers like SLSQP that fail to solve the problem even with a very low amount of noise. Then we did a certain selection here of optimizers that were successful even at some noise level. And what's interesting here is that you have some critical level or some critical noise level where the performance just drops suddenly or sharply. One thing that's interesting and that's actually in line with other research is that for some optimizers, for example, look at NFT here, so the yellow one, a moderate amount of noise seems to help even the optimizer in finding optimal solutions. We believe that this is because if you have a low amount of noise, you're more likely to escape local minima and possibly find directions or like make larger steps on barren plateaus. Okay, now to continue the scaling analysis, you can put a fit to the sigmoid function. We just took an tangents hyperbolic or an hyperbolic tangents here. To sort of analyze the behavior in a more quantitative way. On top, you see the fit function. This is just a normal tangents, a normal hyperbolical tangents, just put with a little bit of different parameters, sort of to identify easier the different limits that you have. So you basically have a no noise performance limit, then you have an infinite noise performance limit, and this is not actually zero because typically, like if you would randomly select bit strings, of course you still have some chance to find the optimal one, so this is not zero. And then you can quantify where the drop is here. And from this, we actually go one step further and look at characteristic quantities that then give us the noise resilience of optimizers. And actually what you're looking here is the point of steepest descent, and this should be clear. Then the slope at steepest descent, so basically how hard the or how sharp the drop is. And the point of resilience. And point of resilience means we look at the point where the sort of success probability has dropped to 90% of the success probability at noise level 0. This is these are basically metrics to just sort of put the noise resilience of the optimizer into one number. Okay, and now we can go back and remember that we did all of this for different system sizes, so from 3 qubits to 10 qubits, and look at these different metrics and see how they behave with system size. And as you can see here, on the left you have a logarithmic scale. It does not seem to matter much at which one you look. You get something that looks a little bit like an exponential decay, though we need to be a little bit careful here because we're only looking at a relatively limited set of system sizes here. So from this you wouldn't be able to really judge whether this is an exponential or power law decay or what it is exactly. So actually we looked at all of these options. First, we mapped actually our sort of Gaussian noise to something called relative absolute error, because if you're looking at additive noise, you have the problem that, of course, the amount of noise that you heuristically add to the cost function in the end needs to be put in relation to the cost function itself. Because if your cost function is between -10 and 10, and you have a noise of 1, this has a different effect than if you have a cost function that is between -1 and 1, and then you add 1 or add a Gaussian noise. So this is to account for that. But then you can basically do exponential fits. Exponential fits, of course, in this graph are just straight lines, or a power law fit, which looks kind of nice here, and identify the fit parameters there, to really get, or to really put a function to the optimizer that tells us, okay, this is the amount of noise that this optimizer can still solve. And then to really link this to actual quantum computers, you can now say, okay, I take the best optimizer, then I map the hardware noise basically to the loss function noise. I can do this statistically, and then see how well can different, or how big are the systems that I can serve on different devices, and to get these sort of lines here. We're looking at one IBM device, which is IBM Sherbrooke, and you see at some point you have this solvable region, and then you have this unsolvable region, and you cross this at approximately 5 to 6 qubits. This is something that should already tell you that this is not very good for this kind of algorithm. But of course, I mean, if you change the noise level by an order of magnitude, all of this changes. But our point is that you need to look at these kind of charts to sort of judge whether your algorithm may be successful or not. We went one step further, and now suppose that we had fault-tolerant hardware. In this case, of course, we don't have noise, but we still have a statistical error. And this statistical error, that is the nice thing about this approach, can still be just handled as Gaussian noise on the loss function. And for this, like the cool thing is we can actually just calculate the statistical error. We know how finite sampling works. You get this error that is or the relative error goes like n to the -1/2, and then you can compare like the heuristic noise that you get from finite sampling to the noise thresholds that we got from our scaling analysis before, even accounting for the different cases. Okay. Of course, if your finite sampling error is lower, then your problem is solvable in this picture. If it's higher, it is not. And now you can actually put a number to the number, or like derive a number of shots that you would need to get this finite sampling or error low enough to be solvable, or like even to be out of this region of quantum disadvantage. Quantum disadvantage is a concept that basically says, okay, we know what the worst classical optimizer is. The worst classical optimizer is just testing out all solutions. So this has an exponential runtime. And if I get some scaling in my quantum circuit that is larger than that, I can be sure that it will never work. And as you can see here, if you have exponential, or like if your noise level decays exponentially, the noise level that the optimizer can still solve, and then you just never get out of this quantum disadvantage. This should be not that big of a surprise. But even if you're going for something like power law or logarithmic scaling, remember that this is really a worst case assumption. You just have this narrow bound, or like narrow gap between between quantum disadvantage and where your algorithm lies, and also and especially if you look at the left at the number of shots that are required, this quickly grows to numbers that are basically infeasible. We're currently not really planning of running like 1 million shots just for one cost function evaluation. So this is where I want to stop now with this analysis. And the sort of general message that we have here is not that variational algorithms can never work, but you really have to look honestly at how it scales. Because I think like over the last 10 years we have we have a lot of algorithms that work well for small instances, or at least reasonably well. But once you look at the scaling, this argument kind of breaks down. And as it turns out, even just finite sampling can lead to a scaling that is bad enough to destroy a quantum advantage if you're not like really doing clever things to get better estimates. So to summarize, these were the contributions of this paper. We have this general framework we showcase here how the scaling should be analyzed in our opinion, or how one way to do this analysis is, and then demonstrate this on a few variational quantum algorithms, even like showing how you can take this further to fault-tolerant quantum computing if you have only finite sampling error. And of course now what we're planning to do now is try this out with other algorithms to perhaps find an algorithm that scales better. Because of course in the end we are looking for quantum advantage and we're not looking to disprove quantum advantage. And then we need to explore strategies to overcome these limitations. And these are better problem encodings because we fixed this here. And then of course non-variational algorithms, where there's always the question, are these always fault-tolerant algorithms? These may also be partial fault-tolerant algorithms. But yeah, this is what we're looking at. And one last point is perhaps then also keeping in mind that optimization is a field where you're basically starting with a classical problem, and in the end you want to have a classical solution. So this might be very different for problems such as quantum simulation, quantum chemistry, where you start with a quantum problem and then you also have a quantum solution, because then you don't need to get the quantum advantage only in between, but you sort of have it ingrained in the problem. Okay, with this, I think my time is up. I thank you for your attention, and hope that you agree with me, and I'm happy to answer questions.
Okay, thank you. Thanks a lot, Benedikt. So there's some time for some questions. I'm sure there are questions in the audience. Please just raise your hand, and then we will unmute you. So maybe I ask something. So I was when you showed the plots of this P95 99. So it seemed that there was a saturation of the threshold. No, before. I think it was before.
These kind of plots.
Yeah, this.
Okay, let's
the next
large
one.
Yeah.
Yeah, and the next one.
So yeah, there.
Yeah, this one here. What does that mean? I mean, it seems that it saturates. It doesn't go to zero so the slope there, it seems to saturate at some value. I mean, the blue is not covered for low noise level. For large N, doesn't seem to vanish. No.
What do you mean exactly?
On the right, the P95, you see
yes.
that, yeah. So the red doesn't take over completely to the left, doesn't. So is that expected? This is the expected behavior.
We were actually also wondering about this, and we're not entirely sure, but think that another thing that you need to look at then is how are the solutions actually distributed. And if you take random QBOs, you sort of get violin shaped plots. And for small problem sizes, actually just have you just have few solutions, so you don't get such a nice distribution. But for large ones, actually, you often have a relatively high probability of guessing relatively good solutions. And this is why we think that this seemingly counterintuitive behavior we see there for larger problem sizes for this P95. Because of course we would also expect that basically if you scale the problem up enough, at some point the weight always takes over.
Yeah. Yeah, I mean, it seems peculiar of these two optimizers. No? I mean, the also P99 is
Your
quite well
NGD, yeah.
behaved. Yeah.
Yes, I mean, and this is of course something that you can look at, and this is in accordance with our other experiments that the NFG optimizer actually works quite well, and NGD here it's somewhat newer, or like was specific to this algorithm, seems also to work well.
Okay. So in the last transparency, when you look at possible ways out, you mentioned better problem encodings. Is this same as saying, for example, is this also would be a warm start?
I think this is not really a problem encoding, but more basically a strategy to overcome this limitation.
Yeah.
I think with warm starting, the question that you have to answer is whether you're still exploring a solution space that is large enough to to really need a quantum algorithm, because that should be the advantage, that you can explore large solution spaces. But then if basically the effective solution space just scales polynomially at some point, then you can just search it classically. I think this is the issue with warm starting, but this is definitely one of the strategies. I mean, not it's not for no reason that people have started looking into this.
Okay. 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 Is there any more question in the audience? Well, it seems not. So I want to thank Benedikt Poggel for his clear exposition, his clear seminar. And I reconvene with you in 2 weeks back in the next opportunity for this seminar sessions of Quantum Spain. Thanks, Benedikt, and thanks, everybody.
Thank you for the invitation.
And goodbye.